Welcome to the Data Hall YouTube channel. In this video, we are going to understand the concept of dummy variable regression. Now, in our previous videos, we have been talking about regression, and we know if we wanted to perform certain quantitative analysis, say for example, we wanted to study the impact of certain quantitative variables on an outcome variable, then we would use regression, and it is a quantitative analysis techniques. But what if we have a categorical variable, or we have a qualitative aspect such as gender, and we wanted to see how gender have an impact on say for example their wages, then how would we perform these regression analysis? Or say for example race of a person, and we wanted to perform certain analysis on this categorical again aspect, or a qualitative aspect, or a car's color, and we wanted to see how car's color would impact its price or its temperature, say just for example. Again, we have age categories. Now age is a continuous variable, but age categories is a qualitative aspect. Say for example, we have an age category of adult, younger people, children. Now these are categories, these are not ages, so these aren't continuous, these are categorical. Or college degrees. Now in all these cases we have a qualitative aspect, and we want to measure its impact on certain outcome variable. Now how do we do that? First, we need to convert this categorical aspect into quantitative terms. Let's just say, in this case, we have a gender variable, and gender having two categories, male and female. So we have generated a categorical variable by the name of dummy male, and we are assigning it a value of 1 or 0. So we have assigned it a value of 1 for male and a value of 0 for female, right? Wherever it is male, we have assigned it a value of 1. So how do we generate this categorical variable? Whenever we would generate this categorical variable, we would assign a value of 1 when that specific qualitative aspect is present. So in this case, because this is a dummy for male, and wherever that aspect is present, we would assign it a value of 1. Now we could have coded it the other way around. We could have generated a dummy variable for female instead of a dummy for male, where in this case we would have a value of 0 for male and a value of 1 for female. Now it doesn't matter whether we do it this way or this way, the conclusion would remain same. The values might change, but the conclusion would remain same. Now the other question might be that why not to have two variables for each, a single variable for each category. So in this case we have two categories. Why not to have two variables? And the issue with two variables is that it would generate issue which is called dummy trap, and we would come back towards that issue later on in this video. But for now, we would simply remember a rule that a variable with m categories, m number of categories, will have m-1 dummy variable. And what this means is gender, in this case, have two categories. So instead of having two dummy variables, because there are two categories, we would have 2-1 dummy variables. Let's take another example of location. We have 4 different locations: north, west, east and south, but we haven't generated 4 different dummy variables. We have generated just 3 dummy variables, and there is one omitted category, which is in this case south. Now again, it doesn't matter which category do we omit, and I would prove in coming slides how it doesn't matter. Now we have generated 3 dummy variables. The first one is dummy for north. We would assign a value of 1 to the person who is working in north, and the rest of the individuals would have a value of 0 for this variable, for this north variable. For this dummy of West, we would have a value of 0 for everything else but for 1 for West, right? So whenever there is West, the person working in West would be assigned a value of 1 for this dummy of West. And similarly, for dummy of East, we would have a value of 1 where a person is working in East, and the rest would be 0. For South, we wouldn't have any variable, right? That would remain the category, but we wouldn't generate a variable. And that's why, because we are following a rule which says we should have m-1 number of variable for m number of categories. So in this case, we have 4 categories, but we have m-1 number of dummy variables. So let's dive in. Let's have an example and let's study the impact of gender on wage. So now we are going to perform certain regression. And in this case, we have a categorical variable of gender. And we are going to understand its impact on wages. So we have this econometric equation where we have our dependent variable, in this case wage, our constant term, and the x1 variable, which is our independent variable. In this case, it's gender, and an error term. Now in this case, because it is a categorical variable, we are going to generate a dummy variable. For this specific example, we are going to generate a dummy of male. So because it is a dummy of male, so wherever there is male in our data set, we would replace it with a value of 1, and we would have a value of 0 for female. Now, how do we interpret these values? We know this 850 is a constant term, it is an y-intercept, and this 450 is a slope term. And if we had a continuous independent variable, then we would have interpreted it that for each 1 unit increase in independent variable, the dependent variable will increase by $450 or units. So in this case, it wouldn't make sense to say a 1 unit increase in gender, right? What would a 1 unit increase in gender look like? So the interpretation is a bit different for categorical or dummy variable. In this case, we would say that this 450 means that male earns $450 higher wages as compared to female. Now why we are saying male earns higher wages? Because this is a dummy of male, because we are assigning value of 1 to male. So we would compare this category with the omitted category. In this case, the omitted category is female. We do not have any variable for female, we just have a variable for male. Now it isn't the expected wages, but this is a differential coefficient, which means that the wages of male are $450 higher than female. Now what would be the expected to know the wages of male, the expected wages of male? We should know what the expected wages of female would be, and that would be in the omitted categories. Expected value would be in the constant term. So in this case, the expected wage for female, which is the omitted category, would be $850, and male's expected wages would be $450 higher than female. So if we do it numerically, the expected wage for when dummy for male is equal to 1, dm is equal to 1, would be 850. We are just copying this equation over here, plus 450, and because this dm would be equal to 1, which is another way of saying that the expected value for male, the expected wage for male, if we simplify this, if we calculate this, we get 1300. Now this 1300 is the expected wages. This is our predicted wage for male. And what is the predicted wage for female? We would say dm, when the dm is equal to 0, and when dm is equal to 0, we mean that we are talking about female, the omitted category. So 850 plus 450 into 0, so 0 multiplied by 450 would be 0. So we are left with 850. That means the expected wages for female are 850, right? And the male's expected wages are $450 higher than female. And if we wanted to represent this graphically, we would use a histogram or a bar chart. Now, what if instead of assigning a value of 1 to male, we assigned a value, we created a dummy for female. Rather than dummy for male, we created a dummy for female, and we would assign a value of 1 wherever that aspect would be present. That means wherever the individual is a female. So in this case, we have the same data. We again run the regression of wage on dummy of female, right? And we get different numbers. Now remember, I said the conclusion would be same, but the numbers can be different. In this case, we get different numbers. Now what this minus 450 would mean? It means that female earns $450 less wages as compared to male. And what would be the expected wages for male? Remember, the omitted categories value is in beta, not in constant term. So the expected wage for male would be $1,300. If we do it numerically as we did before, the expected wage for female, when df is equal to 1, in this case 1 would mean female, is $1,300 minus 450 into 1 would be $850. So the expected wage for female is not $850, and for male, which is df is equal to 0, would be $1,300. These are exact same values. The conclusion is exactly same, but the interpretation of these slopes or the constant term would always be with respect to the omitted category. We would always, these are differential coefficients, we would always interpret them with respect to the omitted category. So this was an example where we just had 2 categories and we have got quite a good understanding of how to interpret them. But what if we have more than 2 categories? So let's understand the impact of location on wages. Say for example, we have 4 different locations: north, west, east and south. And we wanted to see how wages are different or similar, or how wages change with respect to location. Now we would have this equation. We would have dependent variable, the constant term, and the 3 dummy variables for the categories. Although we have 4 categories, but we would have just 3 dummy variables, and that is because we want to avoid dummy trap. In this case, we have a dummy for north, for west and east. For south, we have omitted it, and remember, the omitted categories estimated values would be in the constant term in B0. So how do we interpret this 260 DN? That means that a person working in north would earn $260 higher as compared to south. Now why as compared to south? Why not as compared to west? Because south is the omitted category. So we would compare these values with the omitted category. So $260 higher as compared to south. A person working in west would earn $120 higher as compared to a person working in south. And how much would this person working in south earn? Obviously, it is the omitted categories result are in beta naught. A person working in south would earn an expected wage of $1,040. Now you would have noticed this asterisk signs. What this asterisk means is it represents the statistical significance, whether the results are statistically significant or not. Now, although in previous examples I didn't use asterisks, and that is just to keep the example simple. The asterisk would mean that the results are statistically significant or not. So in this case, the dummy for north do not have asterisk, or other dummies do not have asterisk. So that means these are not statistically significant. That means we would accept the null hypothesis and reject the alternate hypothesis. And in this case, what would be the alternate hypothesis or the null hypothesis? The alternate hypothesis would be that the wages in north are different from the wages in south. And the null hypothesis would be that there is no difference in the wages of a person working in north or south. In this case, because it is statistically insignificant, we would accept the null hypothesis, and that means we cannot statistically prove, or we aren't confident enough, simply saying we aren't confident enough to conclude that the person working in north would have different wages as compared to person working in south. So these are differential coefficients, right? But in this case, we aren't concerned about the asterisk term. We are just focused towards the interpretation, but just I wanted to add a little detail. Now, if we wanted to understand the estimated values, so the estimated value wages for a person working in north, so that's why we have assigned a value of 1 to dn, that is and 0 to others. So that would be 1040. We have simply copied it over here, and we have replaced the values of the dummy variables. So a person working in north would have 1040 plus 260 into 1, the others would become 0. Person working in north would have expected wages of $1,300. What about a person working in west? So the others would become 0, but we would just add 1040 and the dummy of west. So we get expected wage for west, it would be 1160. For east, it would be 1060. The rest of the values become 0. The rest of the categories value becomes 0. And we add the value of east to the omitted categories value, or B naught constant term. What about the south? If all becomes 0, then that means south is having the value of 1. So these all would be 0, and we would be left with the beta naught, which is 1040, the constant term. So that means the person working in south would have a expected wage of 1040. This is what we mean when we say that the results of, or the estimated value of, the omitted category is in the constant term. Now what if, let's move toward dummy trap. Now what if we included 4 dummy variables one dummy variable for each category? So instead of 3 dummy variables, which we have in this case, what if we had 4 dummy variables? What would happen? If we include 4 dummy variables, that is a dummy variable for each category, and we do not omit any category, then there would be an issue which is called dummy trap. And what would happen when we run the regression in our statistical package, it would give us an error. It wouldn't execute the results and would give us the results. It would just give us an error, and it would say that the results are perfectly multicollinear. Right? There is a multicollinearity issue, and that is just because we have included all the dummy variables. And if you encounter that error, you just have to drop 1 dummy variable. Now what if we do it like this? We somehow wanted to include all the dummy variables for all the categories. Then we would have to drop the constant term. Now, if in this equation you can see I've included a dummy for each category, but I have dropped the constant term. And how do you do that? When you run the regression in your statistical package, there would be an option which is called drop constant term, and that means that you are running regression through origin. So you have 2 ways: either you include dummy for all the categories and drop the constant term, or you keep the constant term and exclude 1 category. One more thing is that I'm using the same data, but when I include all the dummy variables for, a dummy variable for each category, I do not omit a category, then the values would be different for the same data, and we would also have statistically significant results. Now why is that? So wouldn't it be nice to have statistically significant results? We would always prefer to run regression through origin because we are seeing statistically significant results. But you would have to understand that the hypotheses in the previous example and in this example are different. In previous example, what we were getting was differential coefficient, and the alternate hypothesis was that the wages for a person working in North is different from the wages person working in South. So they were differential coefficients. So we were testing whether they are different or not from the omitted category. In this case, we aren't testing whether these wages are different or not. They aren't differential coefficients. But what we are testing is the alternate hypothesis is that the B1 is not equal to 0, whereas the null hypothesis is that the B1 is equal to 0, right? So if we are getting significant result, that is, we are rejecting the null hypothesis, which means that the B1 is not equal to 0. So here the null hypothesis and the alternate hypothesis is different from the hypothesis that we had in our previous example. Okay, and the values are also different, but the result or the conclusion would remain same. Now, how do we interpret this 1300? In this case, where we run the regression without a constant term, we won't interpret this as compared to the omitted categories, because we do not have any omitted category. We would say that a person working in North would earn an expected wage of 1300. These are actually the expected values. A person working in South would earn an expected wage of 1160. A person working in South would earn an expected wage of 1040. And if we do it using equation, the expected value of person working in North would be 1300. Expected value for a person working in West would be 1160. For East it would be 1066, and for South it would be 1040. Now these are exactly same values that we got from the previous example, so it doesn't matter, the conclusion would be same. You would get the same expected values, but these are the two ways of dealing with this issue. Now for now, in this lecture we just discussed when we just had one categorical variable in our regression. What if we have two categorical variables? What if we wanted to see that what is the impact of location and gender on wages? Now we have two categorical variables. So when we have two categorical variables, what would the B naught, the constant term, represent? Would it represent the omitted categories of the gender, or would it represent the omitted category of the location? And how would we interpret it? So stay tuned to this channel, and in our next video we are going to interpret the regression results for two categorical variables, and then we are going to see how do we interpret the results of interaction term, how do we construct interaction term, what is multiplicative term, or what is slope dummy and intercept dummy. So these all topics related to dummy variables would be discussed in this series on the dummy variable regression. Thanks for watching the video.